nyuma. Lakini tunasikia vizuri.
No problem.
Yeah.
Let me share my screen. Today we are supposed to work on these conjugacy classes. I think it's the same topic we started on last time before I lost the connection. It was chapter 12.
Yes.
But maybe mmeshasoma mmemaliza bwana. Kama mmemaliza naweza enda to the next chapter. Ama mnasemaje wadau?
Funza tu.
Funza tu. Okay, so we now shift to some group theory. Let's share the screen now. I was trying to track the page. I've tracked the page, so now I can share. So you can see the screen.
Yes.
Yeah, good. So I think we'll just start from the beginning because I can't remember where I dropped off last time. The power just went off and I continued talking maybe for another 15 minutes before I realized. All that time I thought I was teaching. Kumbe nilikuwa najiongelesha tu. I can remove the video. Sometimes the video eats up the bundles if you are using bundles. Okay, so this is our topic for today, conjugacy classes. So suppose we have two elements from a group. Then we define the term conjugate. We say X is conjugate to Y in the group G if this holds, this relation holds. Y is equal to G inverse XG for some element G in the group. So this is going to be the focus of our topic, this definition. So if you run through all the elements of G, you can collect all the elements that are conjugate to X or conjugate to Y rather. No, this conjugate to X. You can collect all the elements that are conjugate to X. And we call these sets the conjugacy class of this element X in G. So this again will be notation that is used throughout. So this X, a superscript capital G, will mean the conjugacy class of X in G, or all the elements that are conjugate to X in G. So what is important again is to show that the two conjugacy classes are either equal or disjoint. So if they're distinct, they are completely disjoint. They have no elements in common. There are two ways to prove. You could prove this using an equivalence relation, but we just use the approach the book uses. So the proposition is given here that for any two elements X and Y in G, either their conjugacy classes are equal. If they are not equal, then they have no elements in common. The intersection will be empty. So to prove this, first of all, let's suppose that they are not disjoint. Suppose you have two distinct conjugacy classes and the intersection is not empty. That means there must be some element Z in the intersection, right? Which should be in both X, the conjugacy class of X and also in the conjugacy class of G. So from the definition of conjugacy, you can find two elements G and H from the group such that Z can be written as G inverse XG. But now this Z is also in the conjugacy class of Y. So you can also write it as H inverse YH for some other element H in G. So if you make this substitution, K is equal to HG inverse, you can reduce this whole expression. You see, if you make X the subject here, to make X the subject, you have to multiply by, is it G inverse on this side and G on this side. Then you have X as a subject because now the G and the G inverse will go. It will be because if you multiply this by G, you lose the G, and if you multiply by G inverse on that side, you're only left with X on this side. So that's how we get this expression. Now, if you make this substitution, K is equal to HG inverse, means then you can write X is equal to K inverse YK. So in which case X will be conjugate to Y. So let's just keep track of this. We picked an element that is in both conjugacy classes. And then we have shown that X must be conjugate to Y. So let's follow the arguments. Suppose an element is in the conjugacy class of G, then it means there must be some element from G such that A is equal to B inverse XB. So anything in the conjugacy class of G can be written in this form. So we picked A from the conjugacy class, so we can write it in this form. But we already have K. We can write X in terms of Y using this expression. So we can make that substitution here. And if we take C to be KB, we can write A as C inverse YC. So what does this mean? It means A is in the conjugacy class of Y. So we picked an element A from the conjugacy class of G and shown that it must be in the conjugacy class of Y. So we proved one inclusion. The conjugacy class of G is a subset of the conjugacy class of Y. So a similar argument, but this time picking an element from YG and showing that it is in XG, will prove this second inclusion. And these two inclusions together lead us to the conclusion that XG is equal to YG. The conjugacy class of X should be equal to the conjugacy class of Y. So what we have shown is that if the intersection is not empty, if they are not disjoint, then they must be equal. So they have only those two options. Either they are disjoint, but if they are not disjoint, they must be equal. So another observation we can make is that every element belongs to its own conjugacy class. So since any element you pick from the group will belong to its own conjugacy class, then it means if you put together all the conjugacy classes, get the union of all these conjugacy classes, you will recover G, because every element will belong to some conjugacy class. So that gives us this corollary that every group is a union of its conjugacy classes, and the distinct conjugacy classes will be disjoint as you observed. So this is the other way of proving this using equivalence classes, but we will not use that for now. So now you can pick up all the distinct conjugacy classes that form the union. And that means you have to pick one representative from each conjugacy class. Since the two elements, the same conjugacy class, will generate the same conjugacy class, you can just pick one representative so that you have a more efficient union. So this has no wastage. You pick exactly one representative from each conjugacy class. Then you have a disjoint union of these conjugacy classes. So these elements that you pick will just be called the representatives of the conjugacy class. So here are some examples. If you have any group, the conjugacy class of the identity element is just the identity element. This is because if you multiply the identity element by inverse, then G on the other side, this will still be the identity element. It won't change. So you can't get any other element in the conjugacy class of the identity element. So that's a useful observation. Now let's pick the dihedral group of degree 3, the symmetries of an equilateral triangle. So these are the defining relations of D6. And this is a list of all the elements in D6. Now, if you run through all the elements of D6, computing this product, so it will always equal either A or A squared. It can't be anything else. So by that, I mean, for instance, you can pick B. You have B inverse AB. This, of course, is equal to A squared. And you can keep doing that for the others. You can, for instance, pick A squared, B inverse, then A, then you have A squared B. You can check that. I'm not sure what this will give us, but I think it will give us A squared. For A, you can check. I think this should give us A. You can double check. Anyway, if you run through all the elements and try to get all elements conjugate, you won't get anything like A squared. So the conjugacy class of A turns out to be A and A squared. And in general, if you have the conjugacy class of B, if you pick any, if you do this, you will always get this, right? A minus 2IB. So if I is if I is 1, for instance, let's take I to be 1. This will be A inverse. A inverse is just A squared, BA. So the claim is that this will be A, the inverse of A squared. A minus 2 is the inverse of A squared. But the inverse of A squared is just A. It's AB. Right? So that is one of the elements in the conjugacy class of B. B itself must be there. Then as you run through the others, you should get so the other one is what? A 5 A B A squared. Oh no, A inverse. Oh, that is when I is 1. You can have I equal to 2 as well. I'm forgetting. So if I is equal to 2, just run through this. The inverse of A squared. Then you have A squared on this side. So what do we have? A inverse of A squared is just A B A squared. So you can simplify this. I don't know what you will get. I suspect you get A squared B. What is B? If you write this as A, B, A, and then A. This one in the middle, you can write it as A squared B. Is that correct? You can double check this letter. I have not double checked. So this A and A will give us A cubed, which is the identity. So we'll just be left with BA, and BA again is the same as A squared B. Is that correct? So that's the next bit we get. So with that, we have exhausted all the elements in the group. We don't have any remaining elements, so there's no point in trying to do any more computations. The only other one, in any case, that is left will be to based on the results we have earlier, you can't get anything outside the group, and we have exhausted them. So this is a complete set of this is a conjugacy class of B in G. So we have established the 3 conjugacy classes for D6, and we list them down here. These are the conjugacy classes of D6. And if you can see that the union of all these will give you the whole of G. So you can write the whole of G as conjugacy class of 1 union the conjugacy class of A union the conjugacy class of B. So where these are the representatives, 1 is a representative here, A is a representative, and B is you can use any representative and it will still work. For instance, I can replace B with AB, or I can also replace it with A squared B. It will still work. Yeah, because we need 1 representative only. So the last statement says that if G is abelian, then every element is the only element in its equivalence in its conjugacy class. So if G is abelian, then every conjugacy class will have exactly 1 element. The next proposition is useful. Let's see what it says. If you have 2 elements in G, if X is conjugate to Y, then X raised to N would be conjugate to y raised to n. So if you know that x is conjugate to y, let's say related to y, then it means x raised to n will also be conjugate to y raised to n. And then the other thing, the important to remember, there are two elements that are conjugate. If x is conjugate to y, then x and y will have the same order. So let's see if we can run through the proof quickly. So this is the property we are going to use. If you have any two elements in G, G, two elements A and B, if you fix G, then G inverse AB can be written as G inverse AG. You just fix an identity element in between A and B, and then you're able to write it in this form. So this is what we'll use now for the powers. So the difference now is that instead of having the same element here, A and B, you have X repeating itself, X, 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 and you keep plugging in the identity element in the form G inverse, and then you can split the product into n such terms. So these two are equal. I think yeah. So now let's move to the crux of the theorem. It says if X is conjugate to Y, then it's possible to write X in this form. And therefore, using this result here, we can write Y raised to N in this form, which means Yn is conjugate to X, Xn. Or if you wish, you can say it the other way around. The relation is symmetric. So Xn is conjugate to Yn. So the last thing is to show that the two have the same order. So if we know the order of X as M, then Y raised to M can be written in this form. But since the order of X is M, this element here in the middle will be the identity. And therefore, the whole thing collapses, becomes the identity. So that means we have Ym is equal to 1. So what's left is to show that M is the smallest positive integer that satisfies this equation. So if you pick any other smaller integer, yr, then y raised to r will be in this form, which cannot be equal to the identity because x raised to r will not be the identity. The reason for that, if you go a little further, if you have this form, if you want to say that x raised to r is equal to the identity, because this is the only way now we can show that m is not the order of y by finding a smaller value of r. If this is true, if this is equal to the identity, then it simply means that x raised to r will also be equal to, with some manipulation, you will end up with this statement. It means x raised to r is equal to 1. But what is the problem with this? This cannot be equal to the identity because you know the order of x is m. So any value that is smaller than m cannot satisfy this. X raised to r for any value r smaller than m will not satisfy this. This is not true. And therefore, it follows that we can't have anything smaller than m satisfying ym is equal to 1. And that forces the order of y to be equal to 1. So are we together up to that point?
Yes.
Good. So we want to figure out how do we compute this is also connected to the stuff we did on group actions. If you run through this, you might be able to restructure it to fit with what we did with group actions. It's not so different. You can actually restructure the whole thing to work through group actions. So this one says let X be an element of G. Then the centralizer of X in G, which is denoted by this. Maybe last time this is where I dropped off, somewhere here. Or it could be, I'm not sure, but I remember continuing for quite a while until I realized there was no power. So this says let X be an element of G. So the centralizer of X in G is denoted by this, and is simply all the elements in G that commute with X. So here X is fixed, but we find all the elements in G that commute with X, and we call that the centralizer of the element X. So, I mean, this is another way of writing it. You just shift this. So it's all the elements of G, such that G inverse, the centralizer is all the elements of G which satisfy this. G inverse XG is equal to X. In other words, no, I think there are no other words. Leave it as it is. I think that's clear enough. It is easy to check that this is a subgroup. So as an exercise, try to check that the centralizer of an element is a subgroup. So don't forget to do this exercise. So the other thing you need to observe is that if X is in the center of G, then the cyclic subgroup generated by X will also be, not the centralizer of G. The cyclic subgroup, all the elements in the cyclic subgroup will also be in the centralizer. Because if you take G, any element in this cyclic group will be of a form X raised to some power, right? So this is true. So if I'm to compute for any element in that cyclic group, if I'm to compute this product, then what does it give me? It will give me X here, the inverse. Then I have X and I have XM. So I can add up the powers. If you add up the powers, you end up with X. Remember, in groups, anytime you're working with groups, if you have A, M multiplied by A, B, this is the same as A, M. Just it's similar to the laws of indices for real numbers. So this established any element in the cyclic subgroup generated by X will be in the centralizer, including X itself. So we already have a subgroup. This is a guaranteed subgroup of a centralizer. So here's a theorem. It says, suppose X is in G, then we can make the following claim that the class, the number of elements, the conjugacy class of X is the same as the index of the centralizer of X in G. That's just the number of distinct left cosets of the centralizer in G. This Lagrange is connected in some way to what we're doing in now, if you apply Lagrange's theorem, you can now write this last bit. The number of distinct left cosets is simply equal to the number of elements in the group divided by the number of elements in the subgroup. Remember, we have agreed that you check that the centralizer is a subgroup. So what does this mean? It means Lagrange's theorem allows us to make the statement that the number of elements in the center, not the centralizer, in the conjugacy class of G must be a factor of the number of elements in G. So let's try to go through the proof quickly. So if you have two elements from G, then this property will be true. I mean, if this is true, what are we proving? Okay, I think let's just go with this. We will need it to prove what we want. So suppose these two things are true. G inverse XG is equal to H inverse XH. Then you can rewrite this as follows. I think that's not too hard to see. But then what this means is that this HG inverse will be in the subgroup. Now, if HG inverse in the subgroup, it means the right cosets of these two right cosets will be equal. So I don't know what we did. I think we did the similar thing in group theory. There's a theorem that says this: if you have AB inverse belonging to a subgroup, H is a subgroup of G. So if this condition is true, then it means the left cosets generated by the right cosets, not left. The right cosets generated by these two elements generated by A and B would be equal. You can show it in the reverse form where if you have A inverse, if it was this, A inverse B is in H. If this is true, then for this second case gives you the equivalent for the left cosets. You have to be careful where the A inverse is, where the inverse is. If it's on the first term, you're talking about the left cosets. If it's in the second term, you're talking about the right cosets. But they're all useful, left or right. So we can now define a function from the conjugacy class, the set of right cosets. So this first part, the map will be defined as you pick anything in the conjugacy class will look like this, but you simply send it to the left coset of the centralizer of X determined by G. So if you use this as your map, then this first part means that map will be injective, right? Because if f, thinking of this as a function, if f of x is equal to f of y, then x will be equal to y. Remember, these arrows are throughout. We are using the equivalent. It means it can go in both directions. So if you started from here, you can still go prove that this will be true. So this confirms that our map is injective. But then from the way it is defined, it's quite obvious that it is surjective. Any left coset you pick here will have a corresponding pre-image in the conjugacy class of X. So the map is injective and surjective, and therefore is a bijection. Now, if you're working with finite groups, anytime you have a bijection between two finite groups or finite sets, in this case, they are not groups, they are sets. This is a bijection between the set of the conjugacy, the number of elements, the conjugacy class of X and the centralizer. And sorry, the right cosets of the centralizer of X in G. So every element is sent to some right coset. But this function, since it is bijective, it means the number of elements in the two sets will be equal. But the number of elements here is just a number of distinct right cosets, which is the index of the centralizer in G. So that's a number of distinct right cosets, but that is by definition just a centralizer. So again, we did something similar in group actions. If you go back, you'll be able to connect the two. So before summarizing the results of the conjugacy classes, so we make some observation. This one claims the following: if the number of elements the conjugacy class is just one, there's only one element the conjugacy class, then it means that for all elements in G, this will be true. G inverse xg will be equal to x. So it means that if this is true, X will commute with all the other elements of a group, and therefore it must be in the center of G. So try to get a distinction between the center of a group. The center of a group is simply the set of all elements that commute with all other elements, and the centralizer of an element in the group is a different set. It's a set of all elements in the group that commute with just this one element X. Always keep track of those two definitions. They can be, it's easy to mix them up. Centralizer and the center. Centralizer will be for an element in the group. The center will be will refer to the whole group. And from the definition, we can confirm that if the conjugacy class of X has only one element, then X must be in the center of it. And that is only one way. It's a two-way. You can see that this symbol means the two are equivalent. So also if X is in the center, then the conjugacy class of an element in the center will have exactly one element. You can still hear me? Yes. Okay. And no one has been thrown out of the class. Let's check. A class is still full. So I think we are up to that point, we are fine. And we can now consolidate this into one result. So if you have these X1 up to XL, the representatives of the conjugacy classes of G, then the number of elements in G can be split into two. Remember, the number of the G is the union of all the conjugacy classes, and the union is disjoint. So, yeah. You can still hear me? My network flipped a bit.
Yes.
Okay. So let me continue. So suppose we pick these representatives of all the conjugacy classes. Remember, we said that if you have then it's possible for you to write it as a, if you have picked the conjugacy classes, then this will run from 1 to L, so that you have a disjoint union. So if this is a disjoint union, then it means the number of elements is simply the sum of a number of elements in each conjugacy class. So you run through I up to L and you have a total. But this can be split further. It can be split into the conjugacy classes, XI, G, where the number of elements, the conjugacy classes is equal to 1. And now the other one is supposed to be 1. Pen is equal to 1. And the second set, where the number of elements in the conjugacy class is more than 1. So you split it into two. They are disjoint because it's either 1 or not 1. Now we already established that this case where the conjugacy classes have exactly 1 element, that will be the same as the center of G, because that is proved in this part. If anything is in the center of G, it means its conjugacy class will have 1 element, and vice versa. If the conjugacy class of this element X is 1, then it must be in the center. So they are the same set. So this one is just the center, so you can take it as the number of elements in the center, the group, which is this first part. And then this one simply adds the sizes of the conjugacy classes for the conjugacy classes that have more than 1 element. And those are the ones that are for the values of X that are not in the center. So this is called I think it's normally called the class equation. So what is interesting is that, or rather what has been mentioned here, is that the center is a subgroup. The center of a group is usually a subgroup, so it must be a factor of G. And at the same time, the number of elements in a conjugacy class we have seen earlier is equal to the index of the centralizer of the element in G, and therefore must also be a factor of the group. So each of these terms will be a factor of G, some multiple of G. It also gives you some hint on trying to find the different conjugacy classes, because you know their sizes or their possible sizes. So now we'll apply this to a specific class of groups, the conjugacy, the dihedral groups. Can I propose a 5-minute break?
It's okay.
So we resume at 9:20. So I think you have had a chance to stretch a bit and you're now ready for awamu ya pili. Are we all back ama kuna mtu bado hajarudi?
Tuendelee na ibada sasa.
Tuendelee. Good. I was also washing my cup so that I sip some tea as I teach. And also when you talk a lot, the throat gets tired.
Yeah,
unless
yeah.
you are a politician.
Or a pastor.
So now we will look at the symmetries of a regular polygon with n sides in general. So that is a D2n. This is the dihedral group of degree n. That is the symmetries of a regular polygon that is n-sided. So these symmetries can be generated by two elements, A and B, with this as the relations that generates the whole group. So you can actually list all the elements as the identity, then the element A, keep going until you get to A raised to n minus 1. So once you have all the powers of A, now you can construct the remaining elements, which will be B, A, B, and this will keep going until you get to A raised to n minus 1. So in total, you'll have 2n elements. The size is 2n. The number of elements in the group will be 2n, and that is a list of all the elements. That there should be a comma here. So this gives you the list of all the elements in B to N. And you can now get any product using these defining relations. So we want to pick elements, and we've already seen the example we have seen is D6. I don't know if you've already seen, and we've been able to construct 3 conjugacy classes in D6. So we want to generalize this. What happens in general? We'll separate the two cases. We'll consider separately the case when n is odd and the case when n is even. So we start with the odd case. What are the conjugacy classes? Now, so consider elements of the form when n is odd. Suppose you consider elements of the form a raised to I. What will the conjugacy classes of this be? Now we know that the centralizer of this element will contain the cyclic subgroup generated by A, right? So now if you have, these are both subgroups, the centralizer is a subgroup, so is the cyclic subgroup generated by A, but we have the following situation. This subgroup may be smaller than this one. They could be equal, but might also be smaller, possibly. That is centralizer, not G. So what we are looking at here is a centralizer. Centralizer in G of AI. So this is true. So that means this must have more left cosets than this one, or right cosets, whichever. So the index of A will be bigger because it's a smaller subgroup. If you divide a smaller number by the size of the group, you'll get a larger number than if you divide it with a bigger number. So the index of the centralizer will be smaller than the index of this cyclic subgroup. but we know that the index of each cyclic subgroup generated by A is 2. All the powers of A, we wrote them down. There were 1, A up to A. So they exactly n minus 1 of them. So it means the index must be 2. It's just half the number of elements in the group. So we've been able to establish that the index of the centralizer of AI in G is equal to 2. But this is precisely the number of, also this value here is also the number of elements in the conjugacy class of AI, right? We established this to be true. This you can look at this part in brackets. This relation is true. Keep that in mind. So that means the conjugacy class of any power of A cannot have more than 2 elements, right? Sijui kama tunaelewana. The maximum number of elements it can have is 2. So let's see if we can actually construct a conjugacy class with 12. We can find those 2 elements, because the maximum can have is 2. If you can find those 2 elements, then we are done. So in general, if you have B inverse AI, B, this is straight from the defining relations. Yeah. So if you raise this to I, this will also be raised to I. Okay. So this one gives you this. So it means the inverse of AI is also in the conjugacy class of AI. So it has exactly 2 elements. So these 2 elements are a subset of the conjugacy class of AI. Now, since n is odd, the inverse of there's no element that's its own inverse, right? It's not possible. No element would be its own inverse since n is odd. I hope that makes sense. If it doesn't, you should ask so that I explain further. So since the 2 elements in the conjugacy class are this AI and A minus I, and they're distinct, then this would be the smallest possible number of elements. There might be more, just we don't know. So that means the number of elements should be greater than or equal to 2. So we have a sandwich kind of thing. We have sandwiched this value between 2. And therefore, it has no option but to be equal to 2. There's a sandwich theorem which says if you have some number and you can show that, say, 2 is less than some number, let's call it n. This is called a sandwich theorem. You can look it up and get the details, but it simply says if you have this means that n must be equal to 2. So that's the similar situation we find ourselves in. And that means the size of any conjugacy class will be 2. But now we've shown that these are the elements in any conjugacy class of some power of A. And therefore, we basically have found them. So so equality holds. The number of elements cannot exceed 2. Now the other must be equal to 2. Not only does not exceed 2, they must be equal to 2. Now, the centralizer of the AI in G is just the cyclic subgroup generated by A. Did I miss something? Why is this true? Why is the centralizer of AI the cyclic subgroup? Because the other elements do not, the other elements will not commute with A. The only elements that commute with A are the powers of A. So it's a cyclic subgroup generated by. So it's only the A's that commute with this one. So the centralizer of this element, AIMG, is just a cyclic subgroup generated by A. And based on this, we have established that the conjugacy class of AI will consist of just the element AI and its inverse. So this gives us all the conjugacy classes of these elements AI. So what's left is to find the remaining conjugacy classes. So these are they're all of size 2, and how many of them will we have? So for instance, if I have A, the inverse of A will be A n minus 1. Next one will be A squared. The inverse will be A n minus 2, and so on, until I get to, since they are being paired, I have to stop at some point. Will it be is it n minus 1 over 2? The last one. Then you have A. Remember, n is odd, so n minus 1 over 2. Will this give us? No, this will not give us. What will be the last one? I need to. So we can try with a simple example. Suppose we are working with if n is 5, then the A will go with A4. A squared will go with A3. Then A3 will go with. Now this is repeated. I think that's it. They will stop here. These are the only ones you'll have. So if n is 5, you have only these two, this one and that one. So what is this value? This is n minus 1 over 2. I think that's correct. And this is what? What do you do with 5 to get this? I think it's just n minus 2. What's the general? You can generalize this, but you get the idea what I'm trying to do. I'm trying to find out how many of these pairs will be. It should be an easy thing, but it's giving me trouble. If you sit down, you will figure it out. So the centralizer of B definitely contains these two elements, 1 and B itself. And now we also know that B inverse A I B will be equal to A minus I. So what this means is none of these elements, no element AI or AIB will commute with B. So none of them can be in the centralizer of B. No such element of the form AI or AIB will commute with B, and therefore none of them can be in the centralizer of B. So that leaves you with just these two elements, 1 and B. The other elements cannot be, and therefore the centralizer cannot have more than this. So it means the index of a centralizer is now n, because the index of the centralizer is just 2n over 2, because the centralizer has only 2 elements. So this gives you n. That means the index of a centralizer has n elements, and therefore also the size of the conjugacy class must be equal to n. So now here we have accounted for all elements. All the elements of this form AI, we have accounted for them because they pair up to make conjugacy classes. And remember, conjugacy classes are disjoint, so these elements cannot appear in any other conjugacy classes. Since they're all taken, the only other elements remaining, we know that the size of this conjugacy class is n, so it must take up these ones. In total, if you put all the conjugacy classes together, you'll end up with n elements. So there are n remaining elements, which must be the elements in this other conjugacy class. Because they are disjoint, and you can't get any elements from outside the group, the only other option you have are these remaining elements. So the conjugacy class of B consists of these remaining elements that are not entirely powers of A. I think that is clear. So similar ideas will be used for the even. So I'll skip the even case. You will look at it in your own time. But we'll look at the result for the even case. So the dihedral group, when n is odd, then the conjugacy classes will be, they are listed here. So I was right. I should have just written this as the inverse. I was trying to complicate things. A inverse up to the last one will be an minus 1 over 2, and it's inverse. So you have the conjugacy classes you have are as follows. This is 1. How many are these? These are n minus 1 over 2 conjugacy classes. So chi pairs. And this is 1 more. So if you add them up, what do you get? They are n minus 1 over 2 conjugacy classes, which are pairs, plus 2. 2 is what? It's the same as 4 over 2. This gives us n minus 3 over 2. So that's how you get this. No, n plus 3, because we have minus 1 plus 4. That should be n plus 3. So these are the total number of conjugacy classes of the dihedral group of the n when n is odd. So if n is even, the arguments are similar. So I will skip the arguments. You will read them on your own. But here again, the pairs will work. The only issue is that you will have one element where m, since n is even, you can write it as 2m. So the element a raised to m will be its own inverse. The inverse of am will be its own inverse. So it will be in its own conjugacy class. Because they are supposed to be pairs, each element and its inverse. But this element will be its own inverse, so it will be in its own conjugacy classes. Then you have, so you have m minus 1 elements on this side. Someone has dropped out. So you have m minus 1 element here, plus these 2. And then there are 2 other, this one and this one. So if you add them up, in total, you'll have m plus 3. You have exactly M plus 3 conjugacy classes, where M is just half the number. M is N over 2, since N is even. So if you want to write it in terms of N, you can replace M with N. So it will be N over 2 plus 3. Conjugacy classes. I will encourage you to go through the arguments carefully and try to follow them. There are just some slight adjustments, but we have what we've done for the odd case can be done for the even case. Where is so I think that establishes we've been able to find all the conjugacy classes of the dihedral group for both cases when N is odd and when N is even. So then what's left is the conjugacy classes of Sn. So we'll use some observation. We studied this last time. We know the following. If you have a cycle, this is a cycle, I1 up to Ik. So for instance, we'll just make this simple. Suppose you have a cycle 1, 2, 3. If you multiply it by G inverse and G right, this turns out to be the same as G of 1, G of 2. So you still end up with a cycle of the same shape. And these will be the elements in the cycle. We did this in group theory. So you can refer to it to get this. So this simply says that if two elements are conjugate in Sn, if an element is a K cycle, then all its conjugates will have the same cycle shape. So this one I will not prove. This one we did in the only difference is in our case we were working with functions like this, but this one is doing the opposite. It's putting G1 without the brackets. So that's the only change, but we did this in group theory. But the import of this is that if you have a K cycle, any element conjugate to the K cycle will also be a K cycle. So that's one trick you carry with you. Now, the other thing also is that the other thing we learned is that any permutation in Sn is a product of disjoint cycles, right? So again, you can show that if now K1, K2 up to Ks are the lengths of the cycles, the factors that are here, their lengths are K1, K2 up to Ks. So again, anything conjugate to X will have the same cycle shape. You can show that. That's what is shown at the next. Using the same ideas, now you just plug in this identity element in between. You end up with the same thing. So anything that is conjugate to X also ends up having the same cycle shape as X. So if X was just a cycle of length K, then any conjugate will be a cycle of the same length as required. And this follows also for if you have disjoint cycles. So the shape, we have, has it been defined? So we will say the shape of this cycle is is as follows. This particular cycle, the length of the first cycle is K1. The length of the second cycle is K2, and so on. We keep listing them until we get to the last K cycle. The length is Ks. So we will say that this is the shape of this this permutation is this. So for instance, if we have a disjoint cycle like 1, 2, 3, and 4, 5, the shape of this cycle is the shape will be 3, 2, and any element that is permutation that is conjugate to this one will have the same shape. So that's the important thing we need to carry with us. I'll leave the details to you. Now, for any permutation in Sn, we make the following claim that the conjugacy class of X will consist of all permutations in Sn which have the same cycle shape as X. I think that's what we've been proving here. So once I find a cycle of length 2, if I want to, I can get its conjugates by getting all the cycles of length 2. Right. So let's check that with S3. When you're working with S3, you have the class that contains only the identity. Then there are 3 cycles of length 2. If you are thinking of D6, because S3 is the same as D6, but in general that is not true. But for when n is 3, it is. So then if you find all the cycles of length 2 will form a conjugacy class, and then the other cycles of length 3. These are all the cycles of length 3. So we end up with 3 conjugacy classes of S3. So S3 was simple. Now, if you pick, let's say, this element in S4, which is a product of these 2 disjoint cycles, then the shape of this is what? The shape is 2, 2. So you just find all other cycles of shape 2, 2. And these are all of them. So this is the conjugacy class of this element. You just keep looking for all the, and it's of size 3. There's no other, this is it, you can't find any other. The other important thing that maybe you need to remember is that disjoint cycles commute. So if you have something like 1, 2, 3, 4, since they are disjoint cycles, it's the same thing as 3, 4. 1, 2. And also the other thing, we said if you have a cycle like 3, 4, this is the same as, it's the same thing as 4, 3. This is exactly the same cycle. So if you write 4, 3, you will be repeating yourself. So as you work on this, keep these things in mind. Then one more thing about what is the word? If you have a cycle, for instance, 1, 2, 3, 4, the same cycle can be written from any point. So for instance, I could start at the point 2. I would still end up, it will be exactly the same cycle, 2, 3, 4, 1. I could also start at 4 and write the same cycle, but now this is what, it's the same cycle, exactly the same cycle. So there are 4 ways to write this. The last one is to start with 3, 3, 4, 1, 2. So these 4 are exactly the same cycle. They're not different. So keep that in mind as you work with this SN. So the next one, makes some bold statement. It says that there are precisely 5 conjugacy classes of S4. We have found one of them here in example 2. And the claim is that the conjugacy classes, these are the representatives, because these are the different cycle shapes you can have in S4. You can have shape 2, shape 3, shape 2, 2, and shape 4. So this one, the shape is 4. This one, the shape is 2, 2. There's no other shape you can have. So based on the shapes alone, you're able to, this is shape 3. Here the shape is 2. Here the shape is this identity. There isn't much to talk about there. So these are the different possible shapes, and each of them represents becomes a representative of a conjugacy class, because all the other elements in the class will be of the same shape. So what's left is to count. How do you count? Number of elements in each of these conjugacy classes. The first one, if you are looking for 2 cycles, you are in S4. So the number of 2 cycles will be 4 combination 2. I think that will be 6 in total. All the different pairs you can pick up will form the 2 cycles. So you end up with 6. So this first one will have 6. This one will have 6 conjugacy classes. So the next one is how many 3 cycles can you get? So the number of 3 cycles is 4 times 2. So you can count it like this. Anytime you want to get a 3 cycle in S4, this is S4. So if I want to get a 3 cycle, I can fix one of the numbers, right? Then I switch around the remaining ones. So for instance, this can be 2 to 3, 3 to 4, if we use this 2-line notation. But now, once I fix this, I end up with 2 possible 3 cycles. So the other 3 cycles that I have left is this 2 can go to 4 also. Four to 3. 3 to 2. Oh, is that correct? 4, 2, 3, something. I think that's the other 3 cycle. Yeah. So if I fix 1, I get 2, 3 cycles. Now I have 4 different elements I can fix. So for each of those 4, I get 2 cycles, right? This gives me 8. That's the second one. So that covers the second cycle shape. All the 3 cycles, there are 8 in total. Then the other one is these ones we have seen, there are 3. We listed them. And the 4 cycles, there are 6 different ones, 6 distinct ones. 4 cycles, remember I told you that if you have a 4 cycle, like 1, 2, 3, 4, this cycle can be written in 4 different ways. It's just the same cycle. But if you have 4 elements, you can arrange them in 4 factorial different ways, which is equal to 24. But in this 24, each cycle is repeated 4 times. Is that correct? So it means essentially you just have six 4 cycles. That's it. So this gives you the number of elements. The conjugacy class of the identity contains only one element. The conjugacy class of cycles of permutations of shape of cycles of length 2, then cycles of length 3, then permutations of shape 2, is it 2, 2, and then cycles of length 4. That gives you all the conjugacy classes of S4. So there's a table here that tries to give the element plus the number of elements in the conjugacy class and also the centralizer of G. The index of a centralizer of G. There's the equation that we wrote back there will help you compute all this. You're able to compute the index of the centralizer of G, the size of the conjugacy class of G, and the representatives for each conjugacy class are up here. Is that making sense?
Yes.
So you can use similar, it might be slightly adjusted, but you can use similar arguments to get your table for S5. So I will, for this alternating group, and I will leave this as an exercise for you, a reading exercise to read about the conjugacy classes of AN. But for now, I think at this point, I think you have the enough information to fight it out. Then you have a number of examples. Plus the normal subgroup case. So this one also says that any normal subgroup must be a union of conjugacy classes. Again, I'll leave that to you. So I think you can read this, the center of the group algebra, but it's optional. But it's good for you to read. So I think that will be the end of this topic. So the next topic we shall attack is characters. What we can do, topics 10 and 11, you can read them on your own. If I examine them, I think it will have to be on a takeaway basis. So that is for your own reading. I will not consider it as part of the examination unless it's a takeaway. That's topic 10 and 11. But you should read them because I probably will get a takeaway question on those two, on those two topics. So the next one we shall get to is the topic on characters. So I don't know whether you want to do this tomorrow or tomorrow you will be busy. Ama pia characters mmeshasoma. You can put me on holiday. If you have already.
Tomorrow is okay, from maybe 8.
So we do 8 o'clock tomorrow.
Yeah.